Very good morning. In the last class, we started current mirror circuits. Okay. So in the current mirror circuits, just we have understand.
Sir, good morning, sir.
Good morning. Yeah. So know the syllabus. What contents we should be learning in this, especially in this module, is basic current mirror circuits and cascade current mirror circuits, active current mirror circuits. Three components: basic, cascade, and common mode properties. These things we should understand. Okay. So as the basics, why we need to go for the current mirror circuits? As I told you, we already studied single stage and differential amplifiers. So where in these two cases we use so many current sources as the load or as the tail current sources. Okay. So whatever the current sources we used in these two cases, generally they act as a resistors, okay, large resistors, so without consuming the excessive voltage headrooms. And we know how can we get a current source operation from a MOSFET. Simply when the gate is biased properly to operate your MOSFET in the region of saturation, that device, that MOSFET can be act as a constant. Okay. So we have so many applications of this current sources, okay, in the analog circuits. So we will discuss now. Okay. So and one more thing, current sources in conjunction with the current mirror can perform useful functions in the analog circuits. Current sources in conjunction with the current mirrors. What do you mean by mirror? As you know, when you stand against the mirror, you can see your object in the mirror. So like I need whatever the current source having the current, the same current should be required or should be produced at some other branches. That is called the current mirror. Whatever the current, exact the same current I should know, I should be generate in some other places of the circuit. Clear? So in this chapter, then usually we are going to discuss about what is the basic current mirror and bias circuits. After that, what is the current mirror and cascade current mirror. So next we need to analyze the current mirror circuits through either small signal and large signal analysis. Okay. Okay. So finally we can that means introduce the biasing techniques for amplifier states. Okay. So what is the basic current mirrors? Output resistance. Any current or any amplifier, if you take output resistance, capacitance, voltage headrooms of a current source, trade with the magnitude of the output current. So generally, the output current of a transistor, of a circuit, of a device is mainly depends on these things: resistance, capacitance offered by the device, and voltage consumed. So we need the trade-off between all these three things to get the what output current. Okay. So these two, if you see the circuit exactly. Already in the last class I have already we discussed, but once again I'm going to do. This is the what? Diode connection. M1 is the, so input is fed to the M1 and this is the diode connected load. And this is the current source. In place of this current source, I can take a MOSFET, either PMOS or NMOS with proper gate bias. So so in this circuit, current source, we can have a PMOS transistor. PMOS transistor. Got the point? So in addition to these issues, several other aspects of current sources are important. What are the aspects? Supply, process, temperature, dependence, output noise, okay, and matching issues, all things. Supply, process, temperature. So supply means voltage. Process means, so we have 5 processes. Already I told you, slow, fast, slow, fast, slow, and typical. So 5 processes and supply and temperature. Generally, we have a tolerance for the supply and temperature. So by that way, you will get the 3 values. Suppose if you want to fix the temperature, room temperature, so 27 degrees centigrade. But there is always some tolerance, plus or minus something. So with this, you will get the 3 temperatures. Similarly, voltage 5 volts, operating voltage is 5 volts. Okay, but usually because of voltage fluctuations, we have a tolerance. Once again, you need to consider the tolerance. Again, the tolerance we always tells with we can represent with the plus or minus something. Again, you will get the 3 voltages. 5 volts means it's 5 volts plus something 5.5 minus something 4.5 like that. So 3 and 5. So 45 corners. Okay, we need to do the device. I don't know. So anything according to the tolerances we have considered. So that what to do? Yeah, these issues also should be take care about them. So here, this is what tail current we use in the differential amplifiers. In the place of tail current source, I can represent an NMOS transistor with proper gate bias. Okay. How should a MOSFET be biased so as to operate as a stable current source? Stable current source, as I told you. So whatever the 2 current sources you have represented with the MOS, 1 MOS and PMOS transistors, they must be flow the stable current. But due to the variations, I told you so many issues, process and voltage and temperature variations. So definitely those current may not be constant. There may be some small changes. But how to make it constant? To gain a better view of the issues, consider a simple resistive biasing circuit shown here. Assume M1 is in saturation, we can write this is M1 is in saturation. First, let us assume M1 is in saturation. This is in saturation. So output current is equal to, so in output current is a function of this voltage. Am I correct or not? This current, this voltage, sorry. Okay, this is the VZ, you can say VZ voltage. What is the VZ voltage? VZ is equal to VDD by R1 plus R2 is the current, is multiplied with the R2 is the voltage. Okay, so I can write this is the VGS, no problem. So now, whenever this M1 is in saturation, you know the saturation current formula. What is the saturation current formula? 1 by 2 VNCYX W by L into VGS minus VGS whole square. But in the place of VGS, what is there? This formula. Okay. Got my point? Yes. So this expression reveals various PVT dependence of I out. So in the previous expression, what is that expression? 1 by 2 VNCYX W by L into VGS VDD by R1 plus R2 into R2 minus VTH whole square. There are so many process and temperature and supply variations because VDD is a supply, may change 5 volts, maybe 4.5 or maybe 5.5, and VTH also supply dependent, some temperature dependent, and VN is a temperature dependent. So all the parameters in the equation, most of the parameters also resistors. So practically every resistance has some tolerance. So all the parameters which included, which are contributing the output current. So definitely, so that depends on the process, temperature, and supply variations. So mostly that depends on PVT. Okay. The overdrive voltage is a function of VDD and VTH. Of course, what is inside the bracket? What is inside the bracket? So VDD by R1 plus R2 into R2 minus VTH square. So inside the bracket that is there. These two VDD and VTH, they are the this is the generally what is inside the bracket is called the overdrive potential. So there are two terms, one is the VDD and one more is the VTH. Okay, threshold voltage may vary 50 to 100 millivolts from wafer to wafer. Means process to process. Furthermore, VN and VTH temperature dependence. If temperature is more, VTH will be more, and what is the one? VN also more. Got my point or not? VN is what? Mobility of the carriers. So mobility definitely so enhanced with the temperature. So this is the thing, and the issue becomes more severe as the device is biased with the small overdrive voltage. Okay, small overdrive voltage means we get the some problem. The design of current sources in analog circuits is based on the copying of currents from a reference, with the assumption that one precisely defined current source is available. Yes, we need to copy a current from here to here, simply. Okay, so if it is not stable, whatever the current you need to copy to the next place, another place. Okay, so the current must be constant. If it is not stable, you don't know how much you are, that means how much current you are getting. Clear? So that first of all in the circuit, you need to assume or you need to decide or you need to design one current source, that is called the reference current source, should be so what? Perfect. Then the same current can be copied to the any other branches. So while this method may appear to entail an endless loop, it is carried out as the so figure here literally. Okay, this is the my current source, reference current source. So myself, I put my all efforts on this current source to design to produce the constant, current, stable current. So this current is copied to here and here. This current is called the I1, this current is called the I2. I need to copy this current to this branch and this branch. This branch current is I1, this branch current is I2. I1 should be I reference and I2 should be I reference. So to copy from here to here, you cannot take a line wire like this. You should be run through the circuit. Clear? Don't say one wire will be connected from here to there, then current will be copied. No. Not like that. Okay. So how do we generate the copies of a reference current? So reference current is what? This is already designed, which can produce the stable one. Okay, that is the reference. How can you copy the reference to the required place? So how do we generate the high out is equal to high reference? This is my question in the circuit. This is my reference current source. This is already okay. Design, and I out should be I reference. That I want. So you cannot take current wire like this. I told you. So this must be. If you want to copy the same current to here, we need a copy circuit. We need a copy circuit. Clear? Yes. If MOSFET, for a MOSFET, ID is equal to, ID means this current. Suppose if you take this MOSFET, ID is equal to always function of the VGS. Clear? Because the VGS is the voltage which controls the what? Which controls the what? Channel. It may be wide or narrow. So that for a MOSFET, ID is equal to function of VGS. We know that. So if you want VGS from this expression, if you want VGS back, if you want to open the VGS from the function, then apply the inverse function. Then VGS is equal to inverse function of ID. Am I correct? Yes. Yeah, that is if the transistor is biased at I reference, then it produces. This is the transistor. Suppose because I reference is the current source here, this voltage is nothing but VGS. VGS, we know. What is the VGS formula according to the previous assumption? Inverse function of the I reference. Inverse function of I reference. Okay, so this is VGS, so that we can say this is this value, VGS value I can write what? F inverse of I reference. Thus, if this voltage is applied to the gate and source terminal of the second one, so here is one more circuit is there. Suppose this is the transistor. Clear. So now this is fed as the VGS. Okay. Then this is the out. I out current. So I out is that is the function of ID. Sorry, VGS. VGS. What is the VGS here? Inverse function of I current. So that I out is equal to function of inverse function of what is that one? I reference. So I out is equal to I reference. Understand? So that is the way you can copy this. This is called the copy circuit. This small one is called the copy circuit here. Okay. See, this is here. I told you the same thing. I out is equal to this one. You will get the from another point of view. Two identical mass devices. This is one this is and this M1, M2, two are identical mass devices having the same geometrical widths and lengths. Okay. So then equate the gate source versus the operator the saturation equal currents. So this is the main concept. You can understand one more thing. So whenever the two transistors having both are identical and having same VGS, definitely their drain currents are also same. Understand or not? Two transistors both are identical having same gate to source voltage, then what? Whose drain currents are also same. That is the logic behind this one. Yes. The structure consisting of M1, M2 in the figure is called the current mirror. In the general case, the transistor need not be identical. That is the theoretical assumption. Basically, here is need not be this one identical. So neglect the channel length modulation. We can write. So this is the current formula. This is and this for this transistor drain current is I reference. For this transistor drain current is I out. You can write the two equations. If you take the ratio of these two, then these two will cancel. These two will cancel. What is that? Then so I out by I reference is equal to WL by 2, W by L of 2 by W by L of 1. Okay. So you can write I out is equal to I reference is multiplied with the W by L of 2 by W by L of 1. Am I correct? Yes. So by this equation, I can conclude that your I out is not depending on any what PVT, process voltage or temperatures, because all are constants. W by L is constant. I reference earlier your I out formula is what? 1 by 2 mu n CVX W by L into what? So VDD into R2 by R1 plus R2 minus VTH whole square formula. So there are so many parameters which strongly depends on the, which shows the impact because of what? Process voltage temperature. But now there is no such influence. So that I can say with this current mirrors, with this concept, your current mirror will work against the PVT variations. Okay. So all are theoretical, but we'll see later. The key property of this topology is it allows precise copying of current with no dependence on process temperature. That's first we know. The translation from I reference to the I out. I reference to the I out translation. The current should be okay copied from reference to the I out. The same current should flow. So merely involves the ratio of device dimensions. I out is equal to I reference is multiplied with the W by L of 2 by W by L of 1. So you can simplify this much again also, because for a technology L is same, so that you can cancel the L and L, then you will get the W2 by W1. Am I correct? Further simplified like that. For a technology L is same. So for both the transistors L is same, you can change the W value. Suppose if you maintain, so both the transistors W widths are same, then what happens? So it becomes 1. Then I out is equal to I reference. If any mismatches, then less or more, I reference will be at the I out. Yes, it is important to appreciate the cause and effect relationship. Cause and effect. Suppose if you take the VGS is equal to F inverse of I reference, and so furthermore at the output. So F of F inverse of I reference is equal to I reference. These two, you know, one is at the M1 transistor, one more at the F2 transistor. M2 transistor. Okay. The former means this one. So we must the generate VGS from I reference. Okay. Where I reference is the cause and VGS is the effect. Okay, because of I reference, VGS value this much. So that VGS will affect with the cause of I reference. So that I reference here, whatever the inside the bracket is called the cause, outside the bracket is called the what? Effect. The first, the second one if you take. So what is the second one? This one. F inverse of I reference is equal to I reference. Okay, so F inverse of I reference of VGS, it generates the F of F inverse of I reference. Okay, here is yes. In this case, the cause is VGS, effect is I reference. Okay, so that is. So with the aid of these observations, understand why a circuit such as that in the figure does not perform the current copying. Here VB is not caused by, okay, I'll show the one circuit. This circuit is not current mirror circuit. Here I out is not equal to I ref, because so this is not the copying circuit. Okay, so because even though this circuit and this device and this device are biased with the same potential, biased with the earlier also same thing, but it is not, because you are not biased with the transistors with the I reference. Earlier this value is how much? F inverse of I reference. This value is how much? Same thing. But now, so VB is independent of this I reference, it is applied. So that it won't work as a current mirror. Current mirror. What does it mean the mirror? So the same current should be, the same current means what? As the I reference, we must be generated. The copy of copy may not be as clear as the original. Okay, one time copy, workable. Second time copy, maybe. Third time, not acceptable. So means, suppose if you thinking that the same current should be copied many places in a long chain of circuits, it is not preferable. Okay, clear or not? So that is the issue. So generally, I out is equal to I reference. The first case. Maybe I reference, I out is not exactly I reference. Suppose I reference maybe the 5 volts, 5 amperes, and I out maybe a 4.99. Clear? So again copying means maybe reduce. Again copying means maybe further reduce. So that many times copy is not preferable in the long chain of circuits, long chain of mirror circuits. So now my question is, find the drain current of M4 if all the transistors are in the saturation in this circuit. This is my circuit. What is saying? I want this current. I4 I can say. Otherwise ID4 you can say. What is this current? So with this circuit, you know, this current is what? I reference. So this is the ID. So this is the I1. So I2 and I3 and I4. So I1 is equal to, of course, I2. Am I correct? Because of current mirror. And similarly, this is I4 is equal to I3. What is I2? What is I2? I2 is equal to I reference. I reference. I can, otherwise I can say I2 is equal to, so I1 is multiplied with, so W by L of 2 by W by L of 1. Am I correct or not? Are you agree with me? Yes. We must, already we have a formula. Must be agreed. So this is the I2 current. I2 is equal to I3. Am I correct? Because both are in the series. I2 is equal to I3. But what is the I4? I4 is equal to, again, I3 is multiplied with what? So W by L of 4 by W by L of 1. Sorry, 3. What is the I3 value? So what is the I3 value? I3 and I2 same. So that this is the I3 value. So you can substitute I4 is equal to I1 is multiplied. So W by L of 2 by W by L of 1 is multiplied with W by L of 4 by W by L of 2. What is I1? I1 is equal to I reference. So that I4 is equal to, so I reference value is multiplied with this much. This much. So W by L of 2 by 1. So W by L of 4 by W by L of 3. Am I correct? So this is the way you can find the current with the M4 transistor. M4 transistor. Got my point or not? Okay.
Yes, sir. Yes.
See here is it. So IDT is equal to I reference is multiplied by W by L of 2 by W by L of 1. Okay. ID, that means I3 is equal to I2 because of both are series. So that I4 is equal to I3 is multiplied with the, so W by L of 4 by W by L of 3. So now substitute the, so I3 value, I3 in terms of I reference. So that is the final one, where it is. Okay. I hope you understand. I already written. Okay. What is saying? So alpha, beta, this is saying alpha and this is saying beta. Then alpha, beta is multiplied by R reference, I reference. Okay. Proper choice of alpha, beta can establish large or small ratios between the I4 and I reference. So when both are equal, I reference and I4 becomes equal. So if this alpha value and beta value equal to 1, if it's less, you will get the less current, less than 1. If it's more than 1, you will get the amplification of current. Understand or not? So I4 is equal to, you can say, so I reference is multiplied with the alpha and beta. If these two values are greater than 1, then I4 is greater than I reference. That is called the amplification. If these two values are less than 1, I4 is less than the I reference. Okay. Suppose this alpha is equal to beta is equal to 1, then perfectly copy. Understand?
Yes, sir.
Yes. Yeah, this is one more circuit. This is the application. This is your knowledge testing. What is this?
Current mirror, sir.
What is the circuit?
Mirror circuit, sir.
Huh?
Mirror circuit.
I think this is the last circuit in the differential amplifiers. It's a Gilbert circuit.
Gilbert circuit. Yes.
This is the what?
Gilbert circuit.
There are two differential pairs. This is the controlled differential pair. For this differential amplifier, what actually here is what? We need the biasing circuits because these are the current sources. Am I correct? So,
Yes, sir.
here is the VB and here is the VB and here is also VB. Tail current and these are the current sources. Got my point or not? Yes. These are the, this is what? Diode connected node, this is the diode connected node. This is current source and this is current source. And this is the current source. All these current source needs what? Bias. Proper bias. Okay, proper biasing is required. So, for providing the biasing, proper biasing for the Gilbert circuit, I took this circuit. This is what? Current mirror circuit. So, current mirror circuit is an application to provide bias voltage to the Gilbert circuit or differential amplifiers. Not only here, wherever, if you take the different circuits, okay, if you take the different circuits, you can take this current mirror to bias it. Clear? The difference there here is, there we already applied VB, but that VB is not independent of the PVT. But here, what happened? Because this is the current mirror circuit. Already we know the relation between the copying current, which is independent of the PVT variations. So that, understand or not?
Yes, sir.
So that, so this current I am giving, this is giving as the biasing for this current source and this current source, similarly for this current source. Sometimes you should forget about what is the type of transistor, what is the ratios, all the things, forget about it. Just basic is what? We need biasing for the PMOS loads as well as NMOS tail current source. I always tell this is loads, no doubt at all. I'm talking about these are loads, of course. For PMOS loads and NMOS tail current source, we need the biasing. From where we can get the biasing? Yeah, this is a circuit which can provide the bias. So, a different pair is biased by means of an NMOS mirror. This is NMOS mirror. For the tail current source means this is, and PMOS mirror for the load. This is the PMOS mirror. This is the NMOS mirror. PMOS constant is NMOS constant. That's why I told you PMOS mirror, NMOS mirror. PMOS mirror provides biasing to the load current sources, and NMOS mirrors provides the biasing for the what? Tail current source. Tail current source. Got my point or not? Yeah, this is here. This is the M0 transistor, M0. M0 means M0. And this is the maybe M1. Okay. So M2, M1, M2, sorry. This is M0, M1, M2, M3, M4, M5, M6. Then you can call it these three in different way. Because this is already, we know this is a circuit where we already say that this is the M1, M2, M3, M4, M5, M6. Then M7. Okay, then M8, M9. So this is the W by L. This is the W by L. What is the ratio of these two? This is the twice of this one. Twice of this one. Okay. So this is the W by L of PMOS transistor. And the current flowing in this one is 0.4 times IT. 0.4 times IT. Okay. So IT, and here is the 0.4 times, that means 40% of the current. This is the current, total current. So IT is this current, 40% here and 40% here. And this is the all of the PMOS transistors. Okay. The device dimensions shown establish a drain current of 0.4 times IT in M5 and M6. Here and here, M5 and M6. Reducing the drain current of M3 and M4 and hence increasing the amplitude. So by this way, the current flowing in the M1 and M2 are reducing. Therefore, the gain is increasing. That point already we discussed in the previous two classes. Sizing issue. What is sizing issue? Device sizing. Device sizing issue. Okay. We'll see. Current mirrors usually employ the same length for all of the transistors so as to minimize the error due to the side diffusion or sidewall diffusion. We know that LD. In the current mirror circuits, the length is of each and every transistor same to avoid the different LDs. What is LD? Lateral diffusion or sidewall diffusion. You know that if the length is, if the original length is L, then effective length is what? So L minus 2LD. 2LD, the same, that LD is the one. In the previous circuit, means the earlier application, we have seen big circuit, that is the current mirror circuit is applied to the differential concept, differential concept. The NMOS current sources must have the same length, channel length as M0. Okay. Whatever the devices are there in the PMOS and NMOS devices there in the previous circuit, or NMOS current sources. NMOS current sources must have the same channel length as the M0. M0 is the beginning. That is called the copy circuit. Okay. So this is because if Eldron is say double 2. So suppose if you change length change, what happens? So generally our L effect is equal to Eldron minus 2 ID, 2 LD, sorry. Suppose it is a twice. If you change the length, then it becomes a 2 times the Eldron minus 2 ID. And it becomes 2 LD. So this is the threshold voltage of short channel devices exhibits some dependence on the channel length. Thus, current ratioing is achieved by scaling only with, not the length. What is saying? VTH, threshold voltage of a device, is strongly influenced by the channel length also. If the channel length is decreases, VTH also decreases. That is to the VTH roll off. VTH roll off. This is the channel length. You should come this direction. Don't go this direction. Length is decreasing means you should come to zero side. From right to left. Okay. So suppose at this your VTH value is this much. As your length of the device is decreasing, your VTH value is like this. This is called the VTH roll off. VTH roll off. See, at this point, exactly at this point, suppose L is here is some x, here is length is x minus something, x minus some a, x minus a. Okay. See, VTH value is quickly down point, sharpen it down. So up to this point, it maintains less or more constant. Don't say constant, but less or more, it's okay, manageable. But when L value is further decreasing, at a particular value of L, your VTH suddenly drops. What happened if VTH drops? Your substitution current is much more. Because substitution current or reverse current is exponential related with the VTH value. Clear? So that's the, so what do you have? VTH should not be fall. VTH should be more. But the problem is what? If the VTH is more, we need to apply more supply voltage to get the channel. That is the problem. But the operation is good. When in the short channel devices, the length is sinking. Length of the device is sinking. So at that time, when the length is sinking, the VTH also decreases. The decreasing of VTH is better for applying the less voltage to make it on. But the problem is what? Reverse currents, subthreshold currents, second order effects will dominate more and more. That is the issue. So you have a ratio. So with the subthreshold current and VTH value. VTH value is small, subthreshold current is much, because they are inversely related. Sorry, they are having the exponential relationship. Okay, minus VTH for this relation, e power. Okay, so that don't touch the length. Don't touch the length, because this is the problem. So what to do? Yeah, always better. I think you are doing in the lab. You are in the lab also. You are doing something, some design. So where we are touching the only double width of the device, not the length of the device. To copy a reference current, I reference, and generate the two I reference. Copy a current, I reference. Okay, I reference is the reference current. Suppose if you want to generate the double of the I reference. Earlier, just we need to copy the same current. Now myself having a question that if you want to multiply, if you want to amplify the current, okay, the same current should be multiplied by some factor and reproduced somewhere, regenerate somewhere. What to do? Start with the width of W reference. That means reference source device width is, let us say, what? W reference for the diode connected reference transistor, and hence choose twice of the W reference for the other device. So like this, see, here is the reference transistor, where forget about the length, because we are not doing anything with the length, so that better leave it. So this device width is how much? Let us say W reference. Suppose to want double of the current, what to do? This device width is twice of this device. So because we know the formula that already. What is that one? I reference is, suppose here is I out. I out is equal to, so I reference is multiplied with what? W by L of 2 by W by L of 1. But I told you, forget about the length. Then W2 by W1. So W2 by W1. So that is called I reference is multiplied with, what is the W2? 2 times the W1. So 2 W1 by W1. Then what is the answer? What is the answer? Yes. Got my point or not? So this is the way you can generate what? Double of the I reference. Yeah. Unfortunately, direct scaling of the width also faces difficulties. Length we have a problem, so that we are not touching it. But come to the width, okay, but there is a small hurdle. What is that one? Direct scaling of width is not, is facing some problems. What is the problems? Corner problem. Corner problem. See, if the corners are poorly defined, and if the drawn W is doubled, the actual width does not exactly double. See, this is the circuit. This is the top view of the transistor. This is the width of the channel. This is the source and this is the drain, of course. The source and this is drain, and this is the width. Sorry. This is the source and this is drain. Okay, sorry. Yeah. So this is the length, width, length and width. This is the length and this is the width. So this is the top view. So here, see, this is the W. See, W is not like this. It is getting like this. Corners, you are getting smooth corners. Because of the smooth corners, W is not same at several places. Okay, you are scaling directly the W, so that you will get the scaling is like this. Scaling is like this. So the W is not exactly W. Clear? So this is the gate corner. This is called the gate corner. This is the upside and this is the gate corner. So W is not exactly, because say here is some W and here is some W and here is some W changes. Clear? So that is yeah. Hence prefer to employ a unit, so that what to do without taking the W also, go for the unit transistors. Okay, so unit transistor means, see, these are the same transistors. This is called the unit transistor. M2 is the unit transistor. In place of one, you have a two transistors. This is called the unit transistors. So unit transistor, and create the copy by repeating such a device. So this is the I reference, and this is the, so two transistors are there, so that the two I reference. Clear? These are the two devices are same. How do we generate the current equal to I reference by 2 from the I reference? Earlier double, now it is off. How to generate? Okay, so in this case, the diode connected device itself must consist of two units, each carrying the half of the I reference. See, this is the I reference current, 2 units of transistors used here, and this is the, so this is the half of, this is the one I reference by 2, this is I reference by 2, copy to this one. So I reference by 2, I reference by 2, I reference by 4. I by 2 means 2 I references. Then this is single, means again you will get the I reference by 2. Number of units. Here 2 units used. That means each unit is carrying the half of the current. So that to produce the 2 double of the I reference, what to do? 4 units should be used. Again here we need to generate the half of the, so single unit should be used. These are the unit transistors. The problem is easy, but the device length or something is more and more because of using of this method technique. So this is the half width devices. The above approach requires a large number of unit transistors with many different currents must be generated. Okay. So this is the another way for this one. Another solution is take 1 unit here, take it as a I reference, take 2 units, it becomes double, and take 2 transistors in so just for understanding purpose, I'm telling you, this is cascoding. It's not an actual cascoding, but I'm saying just for understanding cascoding concept. So this is the I reference is flowing. So this is the series transistors, but this is not the cascading, because the bottom one is in the triode region. Bottom one is in the triode region. This is not the cascade. You can take this or this. If you take this by this way, you can reduce some number of transistors. So it is possible to reduce the complexity by scaling the lengths, but not directly. So this is, yeah, here is the two transistors. This is not the cascading because the bottom device is in the triode region. So whenever the bottom device is in the triode region, you cannot say both are cascading. The bottom should be in the saturation. Yes. So calculate the small voltage gain of the circuit. Small voltage gain. This is circuit. Voltage gain. What is the voltage gain formula? Of course, here. What is the voltage gain formula? So AV is equal to GM into RL. Am I correct? That is the basic formula. So see, the small signal drain current of M1. M1 drain current is, that means you can say I1. GM1 is multiplied with the input voltage. Okay. So I1, this current is in both the devices, the same current is there. So I1 is equal to I2. So I2 is equal to I3 same because of copying. So I2 is equal to I3 is equal to I2. Okay. So that what is the I3 value? So I3 is equal to I2 is multiplied with what? So W3 by or W by L of 3 by, so W by L of 2. Okay. So what is the I1? I2. So I1, I2 both are same. This is that is equal to, I can say. So GM1 into Vin, okay, is multiplied with, so W by L of 3 by, so W by L of 2. Got my point? This is the I3 current. I3 current is flowing in this one. Okay, so that your gain is, voltage gain is what? So our output voltage is equal to, V out is equal to, RL is multiplied with this much, I3. What is I3 value? This much. Substitute. So V out is equal to, V out is equal to, indra V in undu kada, so divide chesandi. V in is equal to, what is the value? So GM1 into RL is multiplied by W by L of 2, 3 by W by L of 2. That's it. This is the gain. See this one. What my point? This is. Any doubt?
sir.
Unda?
లేదు sir.
Yes. I will stop here. You can ask me any doubt. Okay. Hello? Yes, sir. Can you call me after half an hour? I am right now in the class. Okay. So any doubt? No doubt.
Sir, akkada
Understand?
V out by ఏం రాశారు సార్ అక్కడ? V out by V.
Gain అంటే ఏంటంటే ఫార్ములా వోల్టేజ్ గెయిన్ అంటే?
నేను అక్కడ అడుగుతుంది వోల్టేజ్ గెయిన్ V out by Vin is equal to GM1 RL అని రాశారు అంటుంది.
GM1 into RL into W by L
W by L of 3 by W.
2.
Okay. Okay, sir.
Can I stop? You don't doubts, man?
Yes, sir.